start by briefly reviewing the theorem which we started to prove last time. So the theorem, the one-content theorem, was about that, so if you have X represented as a union of open sets A alpha such that they are all pairwise intersection of path connected, and more or less all triple intersection of triples are also path connected. So the first part, which we already proved, is that the map induced by the inclusions of the open set A alpha into X, the star product of the corresponding, the free product of the corresponding push forwards of such inclusions is surjective, and the second part answers the question about the kernel of this map. So the kernel is given by the normal subgroup, which is generated by elements of such form, where J alpha beta is the push forward of a map which is inclusion of A alpha into intersection of A alpha and A beta. So what was so the proof essentially? So we want to show this last statement. We want to show that so if you have a so-called factorization of element f in pi 1 of x, by factorization we mean presentation as a product of elements, so that each of them is pi 1 of certain A alpha. We want to show that any two such factorizations, they are equivalent in a sense that they can be related by the equivalence relation of the following form. So essentially they differ by elements of this normal subgroup M. So we started to show it by, so we first chose a certain homotopy which connects two different factorizations. Homotopy which is a map from a square to X, and we used a certain, we constructed a certain subdivision of this big square into small rectangles, so that each small rectangle is mapped to a particular A alpha, like here. And then we want to consider a map, a certain path in this rectangle which connects left edge to the right edge, and so this path, any such path, we factorize using vertices and chosen maps GV from x0, the base point of x, to the image of this vertex under the map f. So at the end, so we stopped at so considering such factorization of the composition of map gamma of the path gamma r in the square with homotopy map f, and so each factor corresponds to a small edge in path gamma r between two vertices vi minus 1 and vi, and so we can regard each factor as an element in pi 1 of A alpha A, which is a set corresponding to this rectangle, or pi 1 of A alpha B, which is a set where this rectangle is mapped to. So, and of course, so by definition, so this ambiguity is relates. So if you choose this or this gives us two equivalent factorization. Two equivalent factorization by definition of the equivalence relation. So we can make this statement that which we'll use, that ambiguity results in two equivalent factorizations of f composed with gamma r. So this is some element of pi 1 of x. And so another statement which we will need is that factorizations corresponding to pass gamma r and gamma r plus 1 are also equivalent. So how do we see this? So what is the difference between passes gamma r and gamma r plus 1? So gamma r looks something like this. So before, and so gamma r plus 1 it should separate one more small rectangle, namely rectangle gamma r plus 1 from the rest. And so we see that, so this is gamma r plus 1 above, and this is gamma r. So we see that gamma r plus 1 and gamma r are related by homotopy, which stays in r plus 1. So we can deform the passes only by staying, so that at any homotopy parameter we stay in this square gamma r plus 1. But from this it follows that the composition of the pass with f are related by a homotopy in R alpha r plus 1, because this is because the f maps r plus 1 inside inside the open set A alpha r plus 1 by the construction of this movement. So therefore we can if we consider some factorization corresponding to this pass, and we choose so as here we can always choose for each edge here or here in these parts we can choose the elements of factorization belonging to pi 1 of alpha r plus 1 corresponding to this vector. So this shows that indeed these two different factorizations of these two guys are equivalent. Questions? So we chose, so now let me make the following remark. So before we used, let me just come back. So before we constructed a certain subdivision of the square, of the big square, so that each small rectangle maps to a particular open set A alpha. So we can assume that so the S partitions, which means the partitions of the horizontal partitions are such that they subdivide. So at partitions at t equals 0 and t equals 1. So the subdivision of the lower and upper edge are such that say subdivide partitions used in construction of factorizations. F1 till FL and F1 prime till, sorry, what I mean. So the factorizations was this is a factorization which we want to show the equivalent. So let me elaborate a little bit on this. So in this when you construct such factorizations, so as in level we use a certain subdivision of the unit interval. But when we constructed this the subdivision of the square, we also used we use some subdivision which satisfies certain condition. We can always choose this subdivision of a big square such that we can choose intersections of we can choose a finer subdivision that this is always satisfied. So to what this means, if you consider the lower, for example, the lower edge, so which is where the path gamma 0 goes. So it has some vertices here constructed as before, and so at the same time we know that the composition of f with gamma 0 is the same as f, which is homotopic to 1L. And so the fact that this is the partitions used in the subdivision of this big rectangle are subdivide the partitions used in the construction of factorization means that, for example, F1, so the part which corresponds to F1, it contains might contain a few vertices, and so then there will be a part of F2 which contains a few vertices, and so on. So, for example, here will be R1, R2, R3, R4, 5, and so on. And then we can choose, so we can, so let me consider, for example, F2 here. So we can choose, so let's say this is, let me denote it by vi plus 1, vi plus 2, and so on. With I, and so what we want here is that, so here we, for each vertex, we constructed a certain path which is done by GB, which is with a path connecting the base point of X, which is X0, with the image of this vertex under the map F. And so by construction we chose the image, this passes such that the image was both in, so in this, if you consider this particular case, it's both in the image of A alpha 3 and A alpha 4. Right? But we also want to require that image of this guy belongs to, let's say, a beta, such that image of, so here I choose the example here, F2 image of the path F2 is contained in a beta. So each small path here, F1, F2, and so on, is contained in a certain open set in our cover. And so we can always choose that image of, so the path GB corresponding to this vertex contains in all three of them because of the condition that the triple is path connected. Any triple is path connected. So we can always choose that this belongs not only to open sets corresponding to these two rectangles, but also to open set corresponding to this path here. And so therefore factorizations corresponding to gamma 0 as constructed before, for general gamma R we constructed a certain factorization is equivalent to factorization F1 from because for each, for example, for we can relate, if we start with the path F2, we can relate it up to homotopy to a path, to a composition of passes corresponding to this guy, to this edge, then G corresponding to this vertex, the path corresponding to this edge, then G corresponding to this vertex, and so on. Because we can always do this by homotopy staying in this open set. So this is the third fact that we need, and similarly factorization corresponding to the last pass, which is gamma mn, is equivalent to F1 prime. So this is done by the similar argument. So if you consider a path gamma mn, it looks like this. And there will be, so as constructed before, some vertices. So we have factorization corresponding, corresponding to this, so that each edge gives a certain factor, and then we use the fact that this subdivision by the green vertices is the division by green vertices is the subdivision of the division given, which corresponds to factorization by this factorization. Okay, so now we so what we have is, so if we combine the facts from 1 to 4, so by changing, so we can go from gamma 0 to gamma mn, the factorizations F1 L is equivalent to So again, so the main idea is that we kind of separated everything in small rectangles. The homotopy relating paths f and f prime, which are factorized like this. The square corresponding to this homotopy is separated in small paths, and so we move from the bottom path, which corresponds to this guy, step by step. We move to the upper guy, which corresponds to this factorization. And so everything so in each step everything is simple because we can always, so each small square is mapped to a single A mapped to a single A alpha each square. So everything is controlled here. So this finally answers. Any questions? Okay, so let me give a certain rather simple but important example how one can use this theorem. So let X to be what is called wedge product of some topological spaces Y alpha. So what does it mean? Let me remind you what is the definition of this wedge product. So first we want to fix for each index which labels these topological spaces Y alpha, we want to fix some point, which will be known by Y alpha, small Y alpha, and then so by definition this wedge product of topological spaces Y alpha is the union of the topological spaces. You can say this. So I start with disjoint union of the topological spaces, and I quotient it under equivalence relation. So where equivalence relation is such that any pair of these fixed points is equivalent. So one can imagine this, we have essentially we start with some topological spaces, Y1, Y2, Y3, and so on, and we just glue them at a single point. So this was the point Y1 of this guy, the point Y2 of this guy, and so on.
But can we glue them over open sets instead of points? Is this also called the wedge product?
No, I mean here we are really called, we just use points, fixed base points. I mean, of course, you can consider, like, in general portion, you can consider more general given, but here we just use points for each. And so this is a kind of definition of the wedge product in general, but in order to use Van Kampen's theorem, we will need additional assumptions. So we don't want to consider an arbitrary wedge product, we want to consider wedge products which satisfy this condition. We want to suppose that so for any alpha, Y alpha has an open neighborhood U alpha in Y alpha such that U alpha, this open neighborhood deformation retracts to the point itself. Then the statement is a fundamental group of X So let me denote, so let me choose the base point of x0, which is a class corresponding to any y alpha. It doesn't matter which one because they are all equal. Is the free product of fundamental groups of the topological spaces y alpha. These base points y alpha. So how do we prove this using the one-component theorem? So we need, so first we need to choose some open sets which cover space X. So let me choose, so for each alpha corresponding to this index here, we choose open set which is given by wedge product of y alpha with wedge product of this open neighborhoods for all other indices. So for example, here we choose, so for example, A1 in this example would be, in this schematic picture would be the whole Y1 plus a small neighborhood. So U1, U2, U3, from each other guy, we just keep a small neighborhood, which more or less should deformation attacks to a point. So since all these guys, the deformation attack to a single point, then which is also a point which is identified to a point y, identifies the point y alpha here. This means that a alpha deformation retracts to just y alpha. Since all those guys we can contract to a point, this is the whole thing we can contract to just y alpha itself. And this means that the pi 1 of a alpha with also base point x0 is the same as pi 1 of y alpha, right? Because before we showed that if a space deformation topological space deformation retracts to some subspace, so that their fundamental groups are the same. And of course, we can see that the union of all I alphas is the same as X, right? Because in particular, all A alpha contains Y alpha, so when we unite them, we will get the whole X. Now we want to check that the conditions of the theorem are satisfied. So if you consider any pairwise intersection, this will be, of course, this will be wedge product of all U alphas, and the same for any triple. Okay, maybe it's better to choose a different index. This just follows immediately from the construction of A alpha here. And this is contractible because the deformation attacks to a point. So in particular, pi 1 of any pairwise intersection is trivial. And in particular, from this it follows that n in the definition of one-component theorem is a trivial group. Because so this is, as a reminder, this is generated by J alpha beta omega times J minus 1 beta alpha omega, where omega belongs to pi 1 of intersection, pairwise intersection. But since this is trivial, this is also trivial. And then pi 1 of 0. So in general, by Montgomery theorem, is given by the free product of pi 1 a alpha by alpha divided by n. But since this n is trivial, we just get the free product of those groups. So this proves the statement. This is so in particular, for example, so example in an example is that if, for example, x is the Veitch product of S1 with S1, which looks literally like this, it's two circles glued at a point. The fundamental group of x is z star z, which can be sort of generated is just all kind of words of the following type. So if this is generated by A, this is generated by B, this kind of contains, well, to be precise, it's something A and 1, B, 2, 3. Questions? So if there are no questions, let me actually start a new big topic. So we may later return to some questions about fundamental group, but
Is a Wedge product of two logical spaces also free in the theory of two logical spaces?
Well, I mean, you can define a sort of abstract notion of the Wedge product in category. Is this what you want to say? What is the question?
It's a question because, like, we in some sense get like a correspondence that taking the free abelian groups correspond to Wedge product of spaces. So we have the notion of free objects in groups. So does this notion exist also for topological spaces, and the Wedge product is exactly this one? So
well, yeah, you can define kind of the notion of kind of the structure category with Wedge product, and then there will be certain functor which respects the structure. Yes. Functor between category of topological spaces and the groups, where this kind of the Wedge product structure is the group category. Let me start talking about homology. Are there any questions about fundamental group? Okay. So this is another invariant kind of the homology will give us kind of another invariant topological spaces. So let me remind you, so the fundamental groups was kind of, you can understand this is a functor, which, okay, although we didn't kind of, we very briefly discuss what is a functor, but you can send this for any topological spaces. For any topological space, we assign some group. So the homology will be similar. But as you will see, this is always assigned, it's also for the topological space, it will assign some, actually a collection of groups, but it will assign always abelian groups.
What about the covers? What about the covers? Does it make sense to take an algebra or
Yes, here, for example, yeah, you can. So in this case, you can always construct inverse, and here you can always construct inverse. So any, for example, so even for fundamental groups, it's any group can be understood as a fundamental group of some topological space. So-called Algebraic space corresponding to.
It's called, sorry, what?
Algebraic space. So before we proceed, we need to introduce again some definitions. So first, the definition of what is called standard and simplex. So we will denote by delta with index n, and this can be realized as a subspace in n+1 dimensional Euclidean space with the condition on the coordinates components of the n+1 dimensional vector such that their sum is 1, and they are all non-negative. So what are the examples for small indices? So delta 0, it's a subspace of R1 with the condition that just single t is 1, so it's just a point. And, so delta 1, it will be subspace in R2, which is the following interval. And then delta 2 will be a subspace in R3, which is a triangle. So delta 3, so I cannot draw it as embedded in the 4-dimensional space, but let me just draw it the space itself. So this will be a tetrahedron. And so this is kind of the delta n can be understood as the n-dimensional generalization of a triangle. So it has n+1 vertices. So if it's realized like this, the vertices are 1, 0, 0, 0, then 0, 1, 0, so on till the n, which is 0, 0, 0, 1. So in particular, delta n can be understood, so in terms of the vertices, can be understood as again, as a subspace in R+1, which is given by linear combinations of vectors corresponding to the vectors with coefficients satisfying again their sum is their sum is 1 and they're all positive. And so it's useful to use for certain, so for simplex with vectors v0, v1, and so on till vn, it's useful to use this notation. And so this is it's important that the vertices here. So when we talk about simplices, we want vertices to be ordered. So the order here is important. So from definition, it's clear that any n-dimensional simplex can have so can canonically included subsimplexes. So it's for example n minus m subsimplex delta n minus m can be realized in delta n by restricting certain, so we take m of the coordinates to be 0. And so, and then up to relabeling of the coordinates, we exactly, so if we do this restriction, we exactly get the definition of n minus 1 dimensional simplex. So using this notation, this means that we have embedding, we have inclusion of, so this guy is obtained from this original guy by removing a vertex vi1. So this hat means that we remove this from the list, then the vertex vi2 and so on. So we remove m vertices. So for example, if we have simplex again as before, the triangle v0, v1, v2, we can consider subsimplex v0, v1, which is just the edge here, right? So the one-dimensional, the simplices, the one simplices are just intervals. Yeah, this is a, if you remember the definition of the convex hull, yeah, this is the definition, this is a convex hull of vertices vi. So another definition that we want is definition of what is called delta complex structure on a topological space X. So by definition, this delta complex structure is a collection of maps, which is denoted by sigma alpha. So alpha labels runs over some set, over some finite set, let's say, for simplicity. And so each sigma alpha in this collection is a map from some simplex to X. So n depends on alpha. So n is not fixed. Satisfying the following properties.
So you said the number of functions is finite?
Well, yeah, but here we also know it's finite number of these maps. I mean, here what I'm actually doing is we want first to consider kind of a simple, kind of very intuitively simple notion of simplicial homology, but then it will be easier then to define more kind of powerful singular homology. But which doesn't mean this extra structure. But in any case, so first condition is that the restriction, if you restrict each sigma alpha on the interior of the simplex, so for interior, of course, I mean, as usual, interior is the same as simplex itself minus its bound. It should be injective. And moreover, for any x, for any point x in topological space X, there exists unique alpha, index alpha, such that this X belongs to image of some sigma alpha restricted to the interior of this image. So in words, for any point x, there is only one map sigma. It's in the image of only one of this map sigma alpha when restricted to the interior. So here it's important to restrict it to interior.
Sorry, but if we take any point on the boundary of one of these sigma alphas, and we by the second condition we have another one such that this point is in the interior. So doesn't this mean that there will be other points on the interior of the two?
Sorry. What do you mean? Here the interior actually removes the boundary.
I mean, some points will be covered by the boundary of the image of sigma alpha, right?
Yes.
So if we take any one point on this boundary, there should be some other alpha such that.
Yes.
But these two, if these two simplices, there should be some intersection.
Well, the simplices itself, the images of the whole simplices they will have intersection.
Yes.
But the images of the interiors, they don't have intersection. I mean, let me continue. It will be more clear from the other structure. So if you restrict sigma alpha to a face of delta n. By face we mean n minus 1 subsimplix. So for example, if you have a tetrahedral faces, usually the triangle. And if it's a triangle, the face of a triangle is its edge. Is equal to sigma beta for some beta. So when we restrict this map to n minus dimensional subsimplex, which is the face, we will get, so this should be this should coincide with sigma with some other index. Of course, the sigma should be mapped from n minus 1 dimensional simplex to x. And the third property which we want is that about the topology of x, how the topology is related to this simplex structure, delta complex structure. So set in X is open if and only if the inverse image of it on the sigma alpha is open in delta for any. So morally one can understand this that x is obtained by gluing. Gluing means the usual notion of quotient topology by doing simplices along phases. This is the end of the definition. So let me consider an example. So let X be a two-dimensional torus. So we want to introduce a delta complex structure of this two-dimensional torus. So how we, as you remember, we can realize two-dimensional torus starting from a square and considering a quotient by identifying this H and this H, and identifying, well, this H is this H, right? So let me write. So I can split this rectangle into two triangles, and let me call this. So this big triangle I will call sigma 1, and this I will call sigma 2. So by this actually means the image. So this is the image of sigma 1 of delta of the two-dimensional sigma, because this is delta 2. But for simplicity, I won't write this kind of. When I just write sigma here, I will assume that this is the image of simplex of a proper dimension. And let me call. So let's say this will be sigma 3. Again, let me just write it one more time. Sigma 3 of delta 1. This will be also sigma 3 because it should be identified with this. This will be sigma 4, sigma 4. So these are images of one-dimensional simplices, and so this will be sigma 5, and there will be just the rest will be sigma 6. That's the image of delta 0 is just a point. So all these 4 points they identified. Sigma 6, sigma 6. So all in all, we have 6 maps. So 2 maps, sigma 1 and sigma 2 from 2 simplexes. Then there are 3 maps, sigma 3, sigma 4, and sigma 5 from 1 simplex to X, and just 1 map from 0 simplex to X. And for example, this restriction property says, for example, that so if you label vertices here, for example, in sigma 2, we will in this 2 simplex we will label vertices 0, 1, 2. So we can see the sigma 2 restricting on the subsimplex B0, B1. This will be the same as sigma. So again, the first property means that the sigmas they injected on the interiors of the simplices. Here the simplices are triangles, intervals, and points. And the second property means that if you restrict to any kind of subsimplex, we will get some other sigma. Questions? Sorry, questions? So let me denote by delta n of x. So X is a topological space with delta complex structure defined as before to be an abelian group generated by all maps sigma alpha. That is the so arbitrary element of this abelian group is the formal sum of the following form, where the coefficients are integers. Of course, when we add such two formal sums, we just add the corresponding sum the corresponding coefficients here. And then, so once we define this, we can define what is called boundary homomorphism. It's denoted by delta is index n. This will be a homomorphism from abelian group delta n of x to abelian group delta n minus 1 of x. Explicitly it defines its action on, say, sigma alpha. So it's enough to define the action on all the generators, and the generators are maps sigma alpha. So this maps from delta n to x. So we want it, we map it to certain linear combination where I goes from 0 to n, so the coefficients will be minus 1 to the I, and here we'll have sigma alpha restricted. So if this is, again, if this is simplex, sigma alpha maps from simplex with vertices v0, v1, and vn. Here we consider restriction of this guy on a subsimplex where we remove vertex vi as before. And of course, so by the construction of our delta complex structure, this can be understood as a map from delta n minus 1 to x. So this indeed, here on the right hand side we get an element of this abelian group. So these maps, they satisfy the following nice property. So the composition of delta n minus 1 with delta n is a trivial map. First of all, what I mean by this composition, so it's such composition is well defined because if you can see, so delta n maps from delta x to delta n minus 1x, and then we can use delta d n minus 1 to map it first to d n minus 2. So the same as the composition of these two maps is a trivial map between these two abelian groups. So how do we prove this? So again, since so it's enough to show this property on an arbitrary generator, which is some map sigma alpha. So first we apply the first boundary homomorphism, just using its definition. So it will be this definition. So here restriction of sigma alpha to d to a subsimplex where we remove is vertex. And then, so we can use linearity and then apply this map to this guy again, which means that we want to remove, so in this subsequence we want to remove another vertex. And here we actually, so we want to split, it will be different from, like, we want to first consider sum from 0 to I minus 1. This is where we remove a j's index, which is comes before the vertex with index j, which comes so that it comes before the vertex with index I. And then there will be part where g goes from I plus 1 to n, where we remove, so we remove the vertex which is later than is vertex. And here, so since the vertex I is already removed here instead of j we will have g minus 1, right? Because the position will be not j's position as here, but it will be g minus 1's position. So this can be rewritten as follows. With a double sum, so first term will be, so let me g minus j less than I. Yeah, I can write it just a double sum, meaning I sum over pairs of indices satisfying this condition, minus 1 I plus j and the second part will be a sum, double sum where I is greater than j. But now we can see that this is actually up to, so this guy and this guy, they're essentially the same guys, just I is replaced with j, right? So if we replace I with j, here we get the same thing. But you see that this term and this term has overall, they differ by overall minus 1 sign. This is the sum actually is 0. Which
But here there is a minus 1 and
so here, what I mean, so here, I suppose I can consider this term. I just relabel, so this is the sum of all ij's. I can just relabel. I can change this I to j and I and j to all I. So here I will get exactly the same thing as here, but here I'll get the same thing, but with extra minus 1. Any other questions?
What are the elements of the homology group?
Well, everything is. I'll tell you.
Okay, so until now?
I haven't defined yet homology.
Okay.
I define what is the delta complex structure. I define what is the boundary map, but I haven't defined yet what is the homology.
Okay. Neither the operation.
No. I mean, the first part was just motivation. What is it about?
Sorry, in the group we define the delta NX. Is this just a free abelian group generated by the sigma n, or?
Yes, just free abelian group generated by all maps sigma. So, well, here the delta n, it was, so here we define it for fixed n. So this here sigma alphas are considered with maps with delta of this fixed n. But of course, if you consider union, the sum of this abelian groups for all n's. This will be just abelian group generated by all sigma alphas. Any other questions? So let me give the following. So in general, a sequence which this delta n plus 1, so delta n C1 of abelian groups Cn. So this can be just start, like, you can forget what I was talking for a moment, what I was talking before. So here Cn's are just some abstract abelian groups, and deltas are some abstract homomorphisms between them. Such that this is 0 for any n is called chain complex. So before we had an example of chain complex where Cn's were delta n's, and deltas were this D's like this. They were boundary homomorphism. But here this is a general definition. In general, the chain complex can be any sequence of abelian group Cn's, and the maps between them that satisfy these conditions. So from this condition, it follows that in particular that this is equivalent to the statement that the image of Dn plus 1 is inside the kernel of the homomorphism. So the abelian groups Hn, which is defined as a quotient of the kernel of Dn, image Dn plus 1. So since this homomorphism between abelian groups, so this image is of course a normal subgroup. It's any abelian subgroup is a normal subgroup, so we can define a quotient. So abelian groups are called homology. Of the chain complex. So for any chain complex, there is one can consider the homology groups, which are defined like this. They have for any integer, positive integer n, they define like this. in particular, so in the case when Cn is delta n of x, as defined before, so it's a abelian group generated by maps sigmas, and delta n is boundary homomorphism as defined before, such Hn. So we will denote it more explicitly as H delta n x and it's called is simplicial homology of x. So if we have topological space X with this delta complex structure, we can define the simplicial homology. So let me give you an example. So let me return to the case of torus. So we already constructed the delta complex structure. So again, it can be visualized as a manifold diagram. So this was, so maybe not, I'm not sure about the indices. This was sigma 1, sigma 2. Again, by here, I mean the image of the sigmas. This was sigma 3, this was also sigma 3, this was sigma 4, sigma 4. This one simplex, the diagonal H was sigma 5. And this, there was just one zero simplex, which was sigma 6, the same everywhere, because this point is linked to one thing. Okay, and we also want so let me write the order of vertices here. This two simplex 0, 1, 2, and the order in this simplex is 0, 1, 2 again. Okay. So now we want to okay, so let me first write, so what is delta 2 of x? So it's generated by, it's a abelian group generated by sigma 1 and sigma 2. And so delta 1 of x is a abelian group generated by sigma 3, sigma 4, and sigma 5, and delta 0 of x is generated by sigma 6. And for n greater than 2, this is trivial because nothing else. So now we can, so as a abelian group, this is the isomorphic to Z2, and this is isomorphic to Z3. This is isomorphic to Z3 generators. So let me define, consider the, now we want to consider the boundary homomorphism. So again, it's enough to define it on generators. So for example, how delta 2 acts on sigma 1. So we consider sigma 1, and we want to start removing vertices. So if we remove the 0 vertex, we end up with sigma 3. If we remove vertex 1, we end up with sigma 5. the sign is alternating. If we remove the vertex 2, we end up with sigma 4. Now is if we so the same for sigma 2. So okay, removing vertex 0 will give us sigma 4. Then we, with minus, we remove vertex 1, this gives sigma 5. And then removing 2 gives us sigma 3. So you can see this is actually the same. So in particular, you can see the delta 2 of sigma 1 minus sigma 2 is 0. And so it's easy to see there is this is the whole kernel. The kernel of delta 2 is just the free abelian group generated by the difference. It's a linear arbitrary combination, so it's just sigma 1 minus sigma 2 with some orbital integer coefficients. But of course, the image of delta 3 is trivial because there are no three-dimensional simplices. So then it follows that the H2, which is the H2 of T2. So this is the kernel of delta 2 divided by the image of delta 3 is isomorphic to Z. Now, okay, now what about delta 1? So delta 1 acts on this guy, so there is 3 generators. Now we want the action of delta 1 on all the 3 guys. So first delta 1 on sigma 3. So sigma 3 is, so if we remove 0 vertex we get sigma 6. If we remove vertex 1 we get again sigma 6, but it's with minus, so this is 0. So you can see that the same happens for sigma 4. It also will be sigma 6 minus sigma 6 and 0, and the same for sigma 5. So it will be sigma 6 minus sigma 6. So the kernel of delta 1 is just the whole thing, so it's generated by all the 3 guys. So what about the image of delta 2? So the image of delta 2, we saw that this is it's a free abelian group generated by just this element. The same in both cases. So what was sigma 3 minus sigma 5 plus sigma 4, which is the same as isomorphic to Z, and the quotient is Z squared. Finally, what about delta 0? So the D0. So D0 acts only on sigma 6, and it's 0. So D0 is always 0 because there is no minus 1 dimensional simplices. So the kernel D0 is just generated by Z6, sigma 6. And now we want to consider image of D1. So there is no D1 acts always trivial. So the image of D1 is trivial. H0 of T2 is kernel of D0 divided by image of D1. It's isomorphic to Z. So one can write the result like this: Hn delta x, which is here T2, two-dimensional torus, is equal to Z when n equals 0, Z2 when n equals 1, Z when n equals 2, and 0 when n is greater than 2. So this is the end of the
Here we use these explicit sigmas we have. Can't there be another sigmas which we didn't consider? For example, we can divide with two diagonals, and we have now 4.
Yes. So the and the fact is actually in nice. So it's not going to depend on the choice of this. If you use a different triangulation of the torus, you will get the same. You will get isomorphic homology.
But in the definition of the group we said that we will take the free abelian group generated by all the sigmas. So now we have, if we consider, we have other sigmas.
Well, the sigmas are here. We choose all sigmas for a fixed delta complex structure. Okay, if we check from the definition of this homology group of this simplicial homology group, it explicitly depends on the choice of delta complex structure. So it's non-trivial fact that it's for a different delta complex structure with the same topological thing, we will get the same. But this is just, in practice, we and usually in math, people mostly use the so-called single homology. So this will just give you a flavor what is actually what are homology groups and how. So it's not very scale. It can be quite easy. Just the usual notion of the complex and the homology. So you can, if you want to practice, I can leave you this another exercise for home. So you can see the x to be RP2. So it's kind of, in a sense, it's similar to T2, but we identify. So we start with the rectangle, but we identify this h with this h in the opposite direction, and this h with this h also in the opposite direction. And the exercise is to show that. So again, you can choose this delta complex structure by just using this kind of subdivision, this triangulation, and shows that this is equal to z when n equals 0, z2 when n equals 1, and 0 when n is greater. It's an exercise which I leave it to you. But if you have questions, next lecture. But the procedure is like this. But of course, here you have something not just Z, but something Z2. Of course, you can. So how these things can appear is, for example, Z2 can be if you start with can appear if you start something with, for example, generated by A, and you quotient something by generated by 2A, right? That's how Z2 can appear. Okay. So let me have just a few minutes left, so I can let me just define a notion of which we use, singular. Homology. Let me start with a certain. As in for any homology, so we want to start with one defined chain complex Cn. So the nth abelian group will be generated abelian group generated by all continuous maps sigma delta n 2x. So here we don't no other restriction. So here we don't use any delta complex structure. So sigma, we can consider any map sigma from simplex to x. It may not necessarily be injective or whatever, injective. And of course there are infinite number of such maps. So these groups, these abelian groups are in principle, so the infinite dimension. And the boundary map is a homomorphism such that again it's enough to define it on the generators, and the generator is arbitrary continuous map from n simplex to x. So this guy is equal to, so essentially by the same formula. So if this is a map from delta n to x, where delta n has vertices of 0 till the n. This is so here we consider restriction on sigma on a face where we removed is vertex. And of course this restriction will give us some map from delta n minus 1 to x. So starting from some element of Cn, we get a certain linear combination of generators of Cn minus 1, which also an element of this. So this gives a well-defined map from Cn to Cn minus 1. And then singular.
So there is a type just the upper n should be n, right?
Oh yeah, yes, we start simply. We start with 0. The n plus 1 terms we start with singular homology of topological space X is defined as Hn of X is again as kernel of Dn divided by the image of Dn. Again, here we just use the topological space. We don't need any extra structure as for a simple. This is